last week, in last few lectures, we discussed the concept of constraint motion, and we introduced the degrees of freedom and stated the principle of virtual work, and illustrated it with an example. So, for the sake of completeness, today first I am going to show to you that the principle of virtual work is equivalent to this our earlier condition that we used, that for mechanical equilibrium, that is the total force is 0 and total torque is 0. So, now I want to note the word equivalent. It is a special meaning. So, A equivalent to B means if I start from A, I can logically go to B, and the same time if I start from B, I can logically go to A. So, this is the meaning of equivalence. So, I am going to show you in two parts. First, we will consider the case of a single particle or a single rigid body, which we can represent by a point object, and then we in the next part we will take a extended object. So, here is a picture of a, let us consider a point particle, let us say a point charge placed at the center. Now, there are other charges, 4 other charges at the corner of a square, and at the center of the square this charge q is placed. So, because of these other charges, you can see all the charges are positive. So, the total force from this charge on the center charge and this charge on the center charge is equal and opposite. So, they will cancel, and similarly for these two charges. So, this is a equilibrium. The center charge is at equilibrium, total force is 0. So, now consider you a virtual displacement delta r. So, note that delta r is a vector. So, any direction you move this charge little bit in, let us say in this direction, as shown by this little arrow. So, this is the displacement, and you are imagining this displacement is a virtual displacement. So, then it goes to a new position, and in this position this charge will so is closer to the upper two charges. So, the total force is no longer 0. So, it is no longer in the equilibrium position. Okay. So, let us calculate the virtual work. So, here, so the virtual work in this case, so in general if there are, so in this is a case where this point particle is experiencing 4 different charge forces F1, F2, F3 and F4. So, in general there could be more than 4 or less than 4. So, there could be n different forces on a object. So, the total work done by force 1 is F1 times the virtual displacement delta r. Similarly, for other forces. So, the total work is this sigma represents the total. So, this means the sum over all the forces, and since the displacement, so it is the same particle. So, for all these works the displacement part is same, you can take that all this part common. So, you get the total virtual work is given by the total force on the particle and dot product with the virtual displacement. Now, we can sort of take any arbitrary Cartesian coordinate system and write down the total component of total force in the Cartesian coordinate system, and similarly component of the virtual displacement. So, after simplification and applying the dot product rule, we get the component that the total virtual work is the total force in x direction time the component of virtual displacement in x direction and plus the corresponding term in the y direction and in the z direction. So, now, so this is the relation between the virtual work. So, this is work or virtual work, and this is the written in terms of the total force. So, now we have a expression for the total virtual work done on the particle. Now, if I impose force balance condition, that is, you demand that in this equilibrium position the total force is 0. So, that the force is a vector, note that is a vector, which means that each of its x component, y component and z component, all of them must be independently 0, which means the total force on x component is 0, this total force on y component is 0 and total force z component is 0. And then if you put this 0, then this is, you can see that right hand side of this expression gives you 0, that is you get the principle of virtual work, that if you displace, if you give a virtual displacement, then so the condition of equilibrium is that total virtual work must be 0. Note that we are this F1, F2, F3 etc., these are all the external forces, that is we only need to from this calculation it is clear that we only need to consider the forces that do virtual work. Now, if I do the other thing, that is you impose that delta u is 0, that is you impose the principle of virtual work, then we get an equation that is sigma fx times delta x plus sum over total force in y direction times delta y plus sum over total force in z direction times delta z, that is equal to 0. Now, for a single point particle, this x, y and z, these are 3 independent degrees of freedom. So, there is no other constraint on the motion of this particle, as you can see, for example, in this particular example. So, you can see that we can move this center particle independently in the x direction, y direction and z direction. Now, if you have these 3 independent variable and their sum is 0, then so to be precise, they are linearly independent, then it is clear that this coefficient of each of the only way you can have 3 independent p's going to 0, only way it is possible if the coefficient of all of them are equal to 0. That means, it follows that the total force x component, y component and z component must be 0, which means the total force is 0, hence we get the force balance condition. So, in this case there is no separate torque balance condition is not required. So, this shows that we can start from the principle of virtual work and go to the force balance condition of mechanical equilibrium, and we can start from the force balance condition of mechanical equilibrium and go to the principle of virtual work. So, this shows that they are equivalent. Now, if we have a collection of particles, what happens, or a rigid body which are multiply connected. So, you cannot describe them as a single point particle, you have to consider them as an extended object. Suppose the system is in equilibrium, that means total force on each particle I is 0. So, Fi is the total force on each particle. So, if total force on each particle is 0 on particle I is 0, then if I take a dot product which is virtual displacement. So, delta Ri is a, consider you giving virtual displacement. So, each particle or each component of the system. So, and you consider only the particle I, then the since Fi is 0, then the dot product of Fi times the virtual displacement of the particle I is also 0. So, if this is true for each particle in the system, then the total virtual work done on the system of taking all the particles into account must also be 0. Now, this total force Fi you split into two parts, one is this external force which are not constraint force, and the small Fi which are the constraint force. Now, so internal or the constraint force. Hence, from what our from our previous equation, what we have is that, so this total virtual work is now split into two terms. One term that is the contribution from the external force, and the other term which is the contribution from the internal constraint force. And now, we restrict ourselves to the cases where internal constraint forces do no virtual work, So, they are just there to, so remember the discussion, how is it possible. So, this is the condition. So, we have already discussed how different ways this condition is satisfied in a real situation. and also I mentioned that we are ignoring sliding friction, which does work, but we are ignoring all those frictional work. So, then if this term goes away, then it follows that the total virtual work done by all the external forces on the total system, which is given by this particular expression, must be 0, which is our principle of virtual work. Now, before going to the next topic of discussion, let me point out one interesting sort of application of the concept of degrees of freedom, which is intimately related to analyzing this principle of analyzing mechanics problem with principle of virtual work. But this is not the only sort of importance of degrees of freedom. So, this is gives you a lot of insights about the different topics that you are going to study in your respective branches of science or engineering. So, in modern times there is an emphasis of describing the topics that you are going to study not as a traditional way of physics, chemistry, biology or civil engineering, electrical, mechanical, etc., but to look at a complex system perspective. So, what is a complex system? So, the way to understand complex system is to count the degrees of number of degrees of freedom. So, how many number of variables you need to specify one state of your system. So, the more number of variables you need, the more complex is your system of study. The other aspect of the complexity is the nature of the forces acting in the system, that is the interaction between the system and the surrounding. So, sometimes the equations that describe those interactions, for example, in this course the central equation that we are using to describe doing our analysis is the Newton's laws of motion. So, there are two possibilities. These equations, the fundamental equations that govern the behavior of the system, they can be linear. For example, Newton's law, or let us say those of you who are studying electricity magnetism, Maxwell's equations of electricity magnetism, or they can be non-linear. So, these are the two aspects. Now, using these two aspects, we can sort of organize a lot of the topics that you are going to study in your respective curriculum in this in a map, and that gives you a lot of insight, a new way of looking at your syllabus. So, for example, on the x axis here is the number of variables. So, we can start the simpler, and the y axis is the non-linearity of the interaction or the basic laws of laws governing the behavior. So, the simplest systems are 1 degrees of freedom, and some examples are here. So, these are like topics like RC circuit, or in nuclear physics the law of radioactivity. So, the system, so the easy part, so the second, then you can go to a slightly more complex example with 2 degrees of freedom. So, this involves a very important phenomena called oscillation and different kinds of oscillator, which are very important in physics, biology, chemistry, electrical engineering and so on. So, you have linear oscillators and different spring mass system or RLC circuit. Also, the famous Kepler's laws of the planetary motion, the sun, the movement of earth going around the sun, and then you can keep on increasing the number of variables, and you can get different types of problems, such as in civil or electrical engineering and so on. And then when the number of degrees of freedom is very high, then you get lot of very interesting natural phenomena which are called collective phenomena. And here are some examples like coupled oscillation, or different properties of solids, and something called in physics later you will study when you have large number of degrees of freedom, there is a branch of physics called statistical mechanics. And finally, your degrees of freedom can become infinity, which means you are no longer, so you are treating the system as sort of a continuous body, and there you study from with that approach the various wave phenomena such as electricity, electromagnetic wave or elastic wave or water wave, heat wave, sound wave, etc. And similarly, so these are all, you are just a number of variables are increasing, but in some sense they are simpler system, because your basic equations of motions are always linear. So, they are mathematically simpler to analyze. Now, you can go to the other axis and you can sort of add, make the underlying equations more nonlinear, then it will be difficult to analyze. So, what is the point of this sort of map? So, this sort of map sort of organizes your various examples from simple to complex. So, this part where you have a linear equation of motion and small number of degrees of freedom 1, 2, 3 etc. So, this is kind of simple examples. As you increase the number of variables, the other part which is simple is this linear equations of motion and continuum. So, the theory of this kind of phenomena are very simple. I mean, we can sort of describe, because they can be now described by partial differential equations, which we know how to mathematically analyze. So, this is also some sort of a simple region. Now, if you go from linear to nonlinear, so you add nonlinearity in your basic laws of motion, then you encounter some systems which are like you encounter a lot of interesting behaviors such as chaos. And for example, maybe a more familiar example is the pendulum. So, when you have a linear system, the actual pendulum is a very interesting system with lot of interesting motion possible. But when you sort of think of it as a simple harmonic pendulum or simple pendulum, you restrict yourself to the linear regime, which is like, so you assume that your amplitude of oscillation is small, whereas linear an actual pendulum, if you remove the restriction, so that amplitude of oscillation can be anything. So, it can be even let us say 180 degree. Then you have the real pendulum, then this is an anharmonic oscillation, and you can get lot of different behaviors like that. Now, the final thing I want to mention, that in modern times the real challenging areas of science and engineering are what is called this so called frontier. So, this is the region where in this map, where you have both the large number of degrees of freedom. So, there are lot of phenomena. I will mention only two examples. One is earthquake and another is turbulent flow in liquid, and the third is the living life itself, the living systems. So, if you want to study this kind of topic, so this is the most challenging and more difficult to address, because they involve large number of degrees of freedom and their basic governing laws are also non-linear. So, using this concept of degrees of freedom, you can sort of understand why some things are easy to understand and some things are difficult to understand or more challenging. So, now we are going to start sort of one more way to look at the final way to look at the discussion of mechanical equilibrium. So far we have sort of looked at the system a configuration which is at equilibrium, but now we want to know the stability of the equilibrium. So, there are two things possible. So, let me give you an example. This is actually not a very difficult concept, it is a very simple thing to state in mechanics. However, this becomes important because nowadays this simple concept of stability finds applications beyond the normal traditional areas of mechanics, and that is why I wanted to sort of give you a exposure to this topic. Okay. So, let us see what is meant by stability. So, let us say that I have a kind of some object and I am going to imagine that this is a table. So, I am going to place this object on this table. So, this is a configuration. So, if I keep it, and so this is in a mechanical equilibrium condition, because if you for example draw the free body diagram of this object, you see that the total force will be 0, the total force due to the gravity on this bottle of water and the force by the table on the bottle of water, they balance each other. So, the total force is 0, total torque is 0. So, the system is in equilibrium. You can also do the same as I discussed today, that using the principle of virtual work. But this is not the only configuration that is possible. There is, you know, that this is another configuration, and this configuration is also in mechanical equilibrium. So, then you can ask that which of this configuration is more stable, and we know from experience the answer is that this is more stable. Why, you can ask? So, this is from experience, and those of you who are familiar like kind of anticipate where am I going. So, you can say that okay, this is more stable because in this configuration the center of mass is lower compared to this position. In this position, the center of mass of this bottle of water, let us assume that this is at the middle of the bottle, then this middle of the bottle is at something like this height, whereas in this case this is at lower height. So, because the system can lower its center of mass, which means that it can lower its let us say gravitational potential energy. So, this configuration must be more stable. Now, I can ask another question, which is that what happens. So, let us say I take this configuration, if I disturb it from the equilibrium. Now, this is not a virtual displacement, this is a real displacement. If I give a real displacement, what happens? So, there are two possibilities. One possibility is that it can return to its initial original position. So, if I do this, it will come back. If I do this, it will come back. If I do this, it will come back. The other possibility is that it may go away. For example, in this particular case, let us say instead of bottle, if I take this pen, and let us say if I put this pen on this table in this position. Now, you may imagine that if I remove the pen, now it is possible, I mean you can imagine that in principle the total force on this pen, if I draw the free body diagram of this pen, then the total force on this pen in this position can be 0. The force by the gravity and by the table on this pen can cancel each other. But if I remove it, what happens is that the pen falls down. Why? Because in this case, because the tip of the pen is so narrow, it is very difficult to achieve the torque balance condition. So, if I make a disturbance away from this particular configuration, in that case the it sort of goes away, it goes away from this equilibrium position. So, there are these two possibilities. So, if the system return to the original equilibrium position, then that equilibrium is stable, and if it does not return to this equilibrium position, then this is unstable. But note there is a caveat to here, that if I take this bottle on this, now you know that there are more than one equilibrium position. So, if I sort of disturb it for a small, give it small disturbance away from the equilibrium position, it will return. But if I give a large disturbance away from the equilibrium position, it will not return. So, here what we are, when we sort of talking about stability, we assume that our disturbance, this displacement that we are giving are small. So, this is a small displacement. So, this is very simple everyday experience. Now, we want to use this this simple everyday observation to sort of construct some function that sort of describes a kind of so that we can sort of analyze the stability in a more systematic formal way. So, here this is a very powerful concept of an energy diagram. So, suppose we ignore all the friction that is there. So, for the time being imagine there is no friction, and we assume that all the forces are conservative. That is why we are ignoring friction. Now, what do I mean by conservative? It means that we can derive the forces, we can write down the forces acting on the system as a derivative of an energy function or a potential energy function. So, let us say there is a force F acting on the system, and then so it basically mathematically means that you can express this force F as a derivative or a total derivative of some function u, which we call the potential energy of the system. And this potential energy can have different sources, as we will see in the example. Now, for every possible configuration of the system, compute the potential energy, which is a number, which is a scalar, because you see that this is a dot product. So, between the force and the displacement, so it must be a scalar. So, you get a number for every configuration. So, which means, what do I mean every configuration? So, if I take this bottle again, then this is a configuration, and for which we can compute the potential energy. If we disturb it a little bit further, this is a different configuration, and again we get a potential energy. If we do this, I will get a different configuration. So, as I move this away, for every value of the position of this bottle or angular orientation of the bottle, we can compute a potential energy, a number, and then we have a plot of the potential energy profile for different configuration. Then, if the total force is 0, if this is 0, that is the condition of mechanical equilibrium. So, this basically means that the derivative of this potential is 0. So, then the condition of potential energy minimum is basically means that the potential energy is minimum or it can be maximum, because we have only looked at the first derivative, and this is a condition. So, this is a third way to look at the condition of mechanical equilibrium. Now, for the sake of completeness, I must mention that, as you know, that the first derivative 0 does not tell you whether, it just tells you that the potential energy is minimum, total force is 0, but what happens if you sort of disturb it slightly, that really comes from the second derivative of the potential energy, where R is the variable that describes the configuration. Now, as you know that if the this derivative is 0, negative, the second derivative is negative, then this is a stable configuration. Sorry, this is an unstable configuration. If this is positive, then this is a stable configuration, and if this is 0, then this test fails, and we need to check it in a different ways in general. So, we shall use in the next lecture, we shall illustrate this with an example. Thank you.